Hello everyone, and welcome back to Math 220A Mathematical Logic. Lecture 13, Quantifier Elimination in Algebraically Closed Fields. Our aim today is to prove a celebrated theorem of Tarski and Chevalier, establishing a quantifier elimination result for the theory of the field of complex numbers and more generally for arbitrary algebraically closed fields. This is a particularly important and nice example of a theory from algebra. First, let us recall the language of rings. Which consists of two constant symbols, 0 and 1, a binary function symbol plus, a unary function symbol minus, or the inverse, the additive inverse, and a binary function symbol times for multiplication. Next, the axioms of fields. Are given by the following L-ring sentences. So we have for all x, x plus 0 is equal to x. For all x, y, x plus y is equal to y plus x. Commutativity of addition. We have for all x minus x plus x is equal to 0. And we also have that the operation plus is associative. So for all x, y, z, z plus x plus y is equal to x plus y plus z. These axioms express that addition is an abelian group and minus is the inverse, the additive inverse. Similarly, we have the axioms for multiplication. For all x, x times 1 is equal to x. For all x, y, x times y is equal to y times x. For all x, y, z, x times y times z is equal to x times y times z. So the operation is also associative. We also have that for all x, if x is not 0, then there exists y such that x times y is equal to 1. This expresses the existence of an inverse. Hence multiplication on the set of non-zero elements is also an abelian group. And finally we have the axioms connecting the two operations. So we have distributivity. For all x, y, and z, x times y plus z is equal to x times y plus x times z. And we have that 0 is not equal to 1. Let us denote by phi fields the conjunction of these axioms, so of these finitely many L-ring sentences. Then the sentence phi field axiomatizes the class of fields viewed as L-ring structures. Next definition: the theory of algebraically closed fields is the L-ring theory, denoted as ACF for algebraically closed fields, consisting of the field axioms, so the sentence phi fields, and for each n greater or equal than 1, a sentence chi n expressing that any polynomial of degree n has a root, namely, we can take chi n to be the sentence for all z0 through z n minus 1, there exists x such that x to the power n plus z n minus 1 times x to the power n minus 1 plus etc. plus z0 is equal to 0. Note that this is indeed an L-ring sentence because we are using abbreviations to express the powers. So n is fixed, hence writing x to the n is just an abbreviation for x times x times x, etc. n times. Similarly for all the other powers. So altogether, this is a sentence in the language of rings, which says that any monic polynomial of degree n, where any corresponds to quantifying over the z's, which represent the coefficients of this polynomial. So any monic polynomial of degree n, for any coefficients, has a 0. This shows that the class of algebraically closed fields is axiomatizable by an infinite set of L-ring sentences. Example: by the fundamental theorem of algebra, the field of free complex numbers, C, is algebraically closed, hence satisfies the theory ACF. Towards our proof of quantifier elimination for this theory, we will need to recall some facts from algebra, from the theory of fields and rings, which can be treated as a black box, or you can find the proofs in any basic text on abstract algebra, but we will summarize everything that is needed. So, definition: let A be a subring of a field K, which simply means that A contains 0, 1 and is closed under addition and multiplication of K, but not necessarily under division. Then an element A of K is said to be algebraic over the set capital A if it is a root of a non-zero polynomial with coefficients in A. i.e. we have p of little a is equal to 0 for some p, a polynomial with coefficients in a single variable x. This is 1, and 2, if a is additionally an integral domain, which means a is a ring without zero divisors, i.e. elements x such that x is not equal to 0, but x times x is equal to 0. So of course any subring of a field is in particular an integral domain. So given A an integral domain, we will say that an algebraic closure of A is an algebraically closed field K containing A and such that any element of K is algebraic over A. Now we summarize some standard facts from the theory of fields, which we will need in the proof of quantifier elimination. Let A be an integral domain. Then we have the following. 1, there exists an algebraic closure of A. 2, if K and K prime are two algebraic closures of A, then there exists an isomorphism F between K and K prime in the sense of fields, which is the same as the isomorphism of the L-ring structures in our sense of abstract isomorphism of structures, such that, moreover, F restricted to A is the identity. So the automorphism fixes A, the common subset of K and K prime, and provides an isomorphism between K and K prime. So any two algebraic closures of A are isomorphic over A. 3, assume that A is a subring of an algebraically closed field L, then the subfield AL alg, which consists of all elements B in L, such that B is algebraic over A, is an algebraic closure of A, so in particular is itself algebraically closed, Now let FP alg be an algebraic closure of the field Fp with p elements for some prime p, then Fp alg is an increasing union of finite subfields Fn for n varying over the natural numbers. More precisely, for any integer k greater or equal than 1, the set of roots of the polynomial x to the power p to the power k minus x in the field Fp alg is a subfield f p to the power k with p to the power k elements, and the union overall k in n of Fp to the power k gives us the whole field Fp alg. Furthermore, we have that Fpk, the subfield of Fp to the power L, when k divides L, it is enough to take the field Fn to be Fp to the power n factorial. So this gives us a very explicit way to write the field Fp alg as an increasing union of finite subfields. We also have 5 any algebraically closed field is infinite and 6 let k be a subfield of L and let L be a field extension with k algebraically closed field, and let B be an element of L which is not in K. Then B is not algebraic over K. So this fact summarizes all of the basic properties and facts from field theory that will be needed in our discussion. Now we can state the main theorem of today's lecture. Due to Chevalier and Tarski, the theory ACF of algebraically closed fields admits quantifier elimination. Proof. First, we note that a substructure of a field in the language L-ring is precisely a subring. Indeed, it is a substructure in this language L-ring is a subset that is closed under the operations of addition, multiplication, and the additive inverse operation. Hence it has to be closed under addition, subtraction, and multiplication, but not necessarily under division. So we see that substructures correspond to subrings. Then, by the semantic criterion, for quantifier elimination from the previous lecture, we see that it is enough to prove that if we are given K, L, algebraically closed fields, i.e. both K and L are models of the theory ACF, and A is a common subring of K and L, i.e. a common substructure, and phi of x0 through xn is a quantifier-free L-ring formula, then for any tuple A bar in A of length n, if there exists B in L such that L satisfies phi of B A bar, then there exists C in K such that K also satisfies phi of C A bar. So this is just an instance of the semantic criterion for quantifier elimination from the previous lecture, applied to the case of the theory T taken to be the theory ACF, and our previous observation that substructures are precisely the subrings in the language L-ring. By the field theory fact, parts 2 and 3, we have that both K and L contain algebraic closures which we denote Fk and Fl respectively of A that are isomorphic via an isomorphism inducing the identity map restricted to the set A. In particular, this means that if in L we have B satisfying the formula phi of B a bar, such that moreover B was in the algebraic closure FL of A in L, then thanks to this isomorphism we would immediately find C in Fk satisfying the same formula, because phi is a quantifier free formula, hence in particular it is preserved by an isomorphism, and the tuple A remains unchanged because the isomorphism fixes A. So this shows that we can actually replace A by Fk and moreover identify it with its copy FL in L without loss of generality. So increasing A if necessary, we may assume that A is equal to K is algebraically closed in particular and a substructure of L. So now we have that both are algebraically closed. Next, the formula phi is logically equivalent to a formula in a disjunctive normal form, so to a formula of the form disjunction over I conjunction over J chi I J with each formula chi I J in the same variables x0 through xn, either atomic or the negation of an atomic formula. So this has nothing to do with our specific theory ACF in consideration, just a general basic observation that any quantifier-free formula can be written as a disjunction of conjunctions, both finite of course, of atomic or negated atomic formulas. Now, of course, if phi is of this form, then the whole formula is satisfied if and only if at least one of the disjuncts is satisfied. Hence, it is enough to consider the case where phi is a conjunction of atomic and negated atomic formulas. In the theory of fields, simply from the syntactic rules for forming atomic formulas, we see that any atomic formula is equivalent to the formula of the form p of x bar is equal to 0 for some polynomial p of x bar with integer coefficients hence we may assume that phi of x bar is of the form conjunction over some finitely many I from 1 to n, pi of x bar equals to 0, and conjunction over all I from 1 to m for some possibly different natural number m of the negations of qi of x bar equals to 0 for some polynomials pi, qi with integer coefficients. Okay, so we have reduced to formula phi of this very special form. Now, if one of the pi of x0 a1 through an, which are of course polynomials, over k in a single variable x0, is a non-zero polynomial, then since we're assuming that L satisfies phi of B a bar, we would have that in particular B is a solution of each of the PIs, so in particular of the one which is a non-zero polynomial, and so we would have that B is algebraic over K, which implies by the field theory fact 6 that B is already in K, because K itself is, remember we're assuming that K is algebraically closed, hence B has to belong to K, and so we are done. Because we have found a solution in K as wanted, hence we may assume that phi equals the conjunction over all I from 1 to m, the negation of qi of x bar is equal to 0. So the only condition in our formula is that x bar is not a solution to a given finite list of polynomials. But then, by the existence of B satisfying the formula phi of B a bar, we see that each polynomial qi of x0 a bar in a single variable x0 is non-zero, right? Because part of the assumption, since B exists, satisfying the formula phi, it shows that none of the QIs has value 0. So in particular, each of these polynomials is non-zero, but hence it has only a finite number of roots, because each qi is just a polynomial in a single variable, so has finitely many roots. But remember that the field K, which we assuming is algebraically closed, is then in particular infinite, by the field theory fact part 5. Hence, we can find C in K such that C is not a root of any of the finitely many QIs, because each QI has finitely many roots and there are only finitely many of them, but the field is infinite, so it contains an element which is not a root of any of them. But then, by the definition of phi, by the assumption of phi at this point to which we reduced it, we have that K satisfies phi of C A bar. And again, we have found a solution. So this shows that in each of the cases, we could find a solution for this formula in K. So this verifies the criterion. So the theory ACF has quantifier elimination. An immediate corollary, since now we have a description of all of the formulas in ACF up to logical equivalence, we conclude that in any algebraically closed field K, a model of ACF, the definable sets with parameters are precisely the constructible sets i.e. sets given by Boolean combinations of polynomial equations with coefficients in K. This quantifier elimination result also allows us to determine the completions of ACF. The theory ACF itself is not complete, so note ACF is not a complete theory. For example, we have an algebraically closed field C of characteristic 0, and we also have, let's say, a field of finite characteristic P, which is also a model of ACF, but there is a sentence distinguishing these two structures, namely the sentence saying that 1 plus 1 plus 1, etc., P times equals 0. So it holds in FP-Alge field of characteristic P, but doesn't hold in C, of course. Turns out that that's the only abstraction to completing the theory that is specifying the characteristic of a field. To make this precise, we make the following definition. 1 for P prime, we let ACF P be the theory given by the theory ACF together with an additional single sentence of the form 1 plus 1 plus 1, etc. P times is equal to 0. The models of ACF-P are precisely the algebraically closed fields of characteristic P. And 2, we define the theory ACF0 of algebraically closed fields of characteristic 0 to be the theory ACF, the axioms for algebraically closed fields, together with an infinite set of sentences of the form not 1 plus 1 plus 1, etc. P times is equal to 0 for P ranging over the prime numbers. Now we have the following theorem. Let P be a prime number or P is equal to 0. Then the theory ACF P is complete. Proof. First note that any field of characteristic P greater than 0 contains the finite field Fp as a subfield. Now recall the general fact from the previous lecture. If a theory T eliminates quantifiers, M, N are models of T with a common substructure, then M is elementarily equivalent to N. Now, in our case, given any two algebraically closed fields K and L, models of ACFP for P greater than 0, they both contain the field Fp by the previous remark, and so by the general fact, this implies that K is elementarily equivalent to L, because we just proved that ACF eliminates quantifiers. Similarly, if K is an algebraically closed field of characteristic 0, then K contains Q as the subfield. Hence, again, any two models of ACF0 have a common substructure, hence they are elementarily equivalent. So in each of the cases, we conclude that ACFP is complete. Let us discuss a curious corollary of the completeness of the series of algebraically closed fields of a given characteristic, the so-called Lefschetz principle, which allows to transfer statements that hold in fields of characteristic 0 and those which hold in all fields of sufficiently large finite characteristic. So let phi be an arbitrary L-ring sentence. Then the following properties are equivalent. 1. The field of complex numbers satisfies phi. 2. There exists an algebraically closed field of characteristic 0 in which phi is satisfied. 3. Any algebraically closed field of characteristic 0 satisfies phi. 4. There exists a natural number n such that phi is satisfied in any algebraically closed field of characteristic P greater than capital N. And 5. There exists an infinite set of prime numbers P such that for any prime number little p in the set, there exists an algebraically closed field of characteristic P in which phi is satisfied. So all 5 of these statements are equivalent. Proof. So first note that 1 is equivalent to 2 is equivalent to 3 are all immediate by the completeness of the theory ACF 0. Let's show that 3 implies 4. Note that the theory ACF 0 is equal to, as we just defined it, ACF together with the sentence chi p for p prime, where chi p expresses that 1 plus 1 plus 1, etc., p times is not equal to 0. Then, if ACF 0 implies some sentence phi, by compactness theorem, there exists a finite subset delta of sentences from ACF 0 such that already this finite subset delta implies phi, but this set delta contains only a finite set of sentences chi p, so only for finitely many primes p, so there exists natural number n such that k satisfies delta for any algebraically closed field k of characteristic p greater than capital N. And for such a field, since delta implies phi, we have that k satisfies phi. So this shows 4. Now the implication 4 implies 5 is straightforward. And we show 5 implies 3 to close the sequence of the equivalences. So assume we are given the situation as in 5. Then for p, a prime in the set capital P, we let kp satisfy ACF p, so a field of algebraically closed field of characteristic p, such that kp satisfies phi. So such a field kp exists by assumption. Now if ACF 0 doesn't imply phi, then we have that ACF 0 must imply the negation of phi by completeness of the theory ACF 0, but then by the implication 3 implies 4, there exists some natural number n such that not phi is satisfied in any algebraically closed field of characteristic p greater than n, but then we would have that p must be finite, and this is a contradiction. So this shows that 3 holds and concludes the proof of the Lefschetz principle. Thank you very much for your attention.